Hello and welcome to the third and final part of the fourth lecture of Tripoli 23. In the previous part of this lecture, we discussed uh, the potential function due to a system of charges or a distribution of charges, rather. And I showed an example of solving the potential field due to a circular ring. Okay. So in this part of the lecture, let's look at how we can solve for the electric field given a uh, potential function. Right? First, let's go over a property of the potential field. So recall that work done moving a point charge from point B to point A is not dependent on the path taken. What does that mean again? If you have a point A and B in space, doesn't matter which path you take when you integrate the work done going from point A to point B. Okay, the end result will only matter with the initial and the final state of your movement. Okay? If your movement went from point A to point B, then back to point A, okay, there's no work done on that case. Okay? So if we move around a point charge and place it back to its original position, there is no work done. That is, your closed loop integral of your electric field dotted to its path is equal to 0. Okay? Closed loop integral, so it's denoted by this circle right here on the integral operator. You have seen that already, but you've seen it in Gauss' law, which is a closed surface integral. In this case, it's a closed loop integral. And basically, you have your point right here. You go around some path back to the point you have your closed loop. And you should be familiar with this because that closed loop is normally a circuit loop. Okay? It's normally a circuit loop. If you have something like this, you start from this path, this point in the path, and go around that point and go back. The sum of the voltage is equal to 0. Okay? And that's where the Kirchhoff's voltage law actually came from. Actually came from this equation and due to the property of your electric field. Okay? So some remarks, this is only valid for what we call the electrostatic case. And it's actually the basis of all of Kirchhoff's voltage law or KVL. That's what I mentioned earlier. And in general, a vector field a vector field that satisfies the condition above is what we call a conservative field. Okay? Conservative field is basically uh, if you get a closed loop integral of that field, it will be 0. Okay, next, let's go to the concept of your potential gradient. Okay, so recall the potential field equation right here, the relationship of your voltage and your electric field. Given an electric field E, the potential V can be derived or determined. Is it possible to reverse the process to solve for the electric field given your voltage V? That's your answer. There's your answer. Just differentiate V with respect to L. But wait, L is a vector. How do you differentiate a function, a scalar function, with respect to a vector? So consider then a region in space where an electric field exists. The potential delta V across a very short segment, delta L, on this segment right here, may be approximated by this equation right here. Okay? So your differential voltage is equal to negative E dl cosine theta, where theta is the angle between the electric field and your path. Okay? So your delta V is equal to negative E delta L cosine theta. So the electric field from this point to this point, very small change in distance or change in length, we assume that the electric field is constant. Okay, so the change is just very small, therefore the electric field is constant. So if we get delta V over delta L, which is approximately dV over dL, it's equal to negative E cosine theta, or the angle between your uh, cosine of the angle between your electric field direction and the direction of your path. So comments dV over dL is the rate at which the potential is changing with respect to the distance. Okay? It's maximum if you're going in opposite directions, and that is the case when you have your maximum electric field. Okay, so basically the maximum value of the change in potential with respect to space is equal to the magnitude of your electric field. Okay, so that's what I said earlier. The first remark here. So the electric field intensity magnitude is equal to the maximum rate of change of potential with distance. The direction of dV over dL is maximum is opposite to the direction for electric field, or in other words, basically the direction of electric field is opposite to the direction in which the potential is increasing the most rapidly. Right? So now we define what we call the gradient of a scalar field. I've shown this to you in the previous lecture when I introduced the del operator. So this is where it comes in actually. The gradient of a scalar field T is defined by this function right here. Okay, so let's break it down. T is your scalar field. The gradient of T is a vector field with direction an, okay, the unit vector normal to the equipotential surfaces of T and pointing towards increasing T. Okay. Your dt over dn is the rate at which T is changing in the direction of an, and the direction of the gradient of T is the direction of maximum space rate of increase of T. Okay, so the direction always points to the maximum rate of increase of your scalar field. And the magnitude of the gradient is basically the maximum value of this rate of increase of T with respect to the space it moves around. Okay. So it sounds familiar. It's actually this equation right here, but the direction is just added. Okay. So how do you relate then the three-dimensional electric field to your dimensionless potential field? How do we use the gradient then? So first, consider the differential element of V. Basically, your differential element changes in three directions, X, Y, and Z. So the differential of V is actually equal to the sum of the partial derivative of V in the three directions multiplied by the change that is going into that direction. Okay? Since dV is equal to negative E dot dl, and E is expressed in Ex Ax hat, there's an X component, Ey Ay hat, Y component, Ez Az hat, your Z component, dotted to your Cartesian differential Cartesian length. Okay? It results into this expression right here. So, sorry, comparing the values of this to this, you'll get these three separate expressions. Okay? So the X component of the electric field is basically defined by the change of the voltage with respect to a change in the X direction. As you move along X, if your voltage or if your V changes in value, it means there's an electric field present in that direction. Okay, that's how you can interpret this equation right here. Same is true with the y component and the z component. So summing that all up, it is shown then that your electric field, so just substitute the values, is equal to this expression right here. The change in voltage over the x direction multiplied to ax hat. That's the x component. The change of your field, scalar field voltage, or the voltage field respect to y multiplied to the unit vector along the y direction, and your the change in your voltage along the z direction multiplied to the unit vector in the z direction. Okay? And we know that E is equal to negative gradient of V. So the gradient of V is equal to that expression as we got it, which is equal to del, which is a vector operator multiplied to your scalar field V. Finally, we get this expression right here, where the electric field is equal to negative of the gradient of the voltage. So basically, if you have a potential field V, you can solve for the electric field anywhere in space by getting the gradient of that scalar field. Okay, so you can get your vector field through a scalar by using the gradient. Okay. So as we use the equation on the right to get the voltage from a given electric field, we can use the equation on the left to get the electric field for a given potential. Okay? So this is actually the third method of getting the electric field due to a distribution of charges. But in this case, you have your potential, you have your potential field and convert it to an electric field. In other cases, for method 1, we have a system of charges. We can directly solve the electric field, but it's very hard, and you integrate in 3 directions. For your second method, we have Gauss law, where you enclose a distribution of charges with a symmetric surface, but it only works in symmetric distributions. Finally, we have the third one, which I've shown you. You have a scalar field, and you just get the gradient of that scalar field. You can get the electric field expression. For example, consider then an electric dipole. What is an electric dipole? It's a pair of points of equal magnitude of charge but opposite in sign. Okay. Let that be centered at the origin. They have a distance d between them. Okay. Determine the electric field and potential field at a generic point P located far, okay, far from the middle of the dipole here. Okay. So first you need to derive first the potential field, then get the electric field from that. So the potential field is easier. So how to get that? Well, you just use the equation for the individual potential of the point charges right here. This is for Q1, this is for Q2. And just merge the equations, you'll get this expression at the bottom. So if the point P is very far, we can approximate the distance vectors to be approximately parallel to each other. Therefore, these two equations right here hold true. Okay? So the vector r2 minus r1 is actually approximately equal to d cosine theta, where theta is the angle between r and your point P. Okay? R1 times R2 is approximately the magnitude of R squared, or the distance of point P from the center of the dipole. So we can now simplify this expression of your voltage to this. QD cosine theta over 4 pi epsilon sub 0 times R squared. You can now solve for the electric field by getting the negative gradient of the scalar field. Since we're using it, we're expressing it in spherical coordinates, The gradient of a spherical coordinate is something like this. Okay? So you see you have a change in voltage with respect to the radius, a change in voltage with respect to the arc length along theta, and a change in voltage with respect to the arc length on a circle that is parallel to the xy plane on the sphere. Okay? So that's how you interpret these three terms on your gradient for your spherical coordinate system. All right. Now, since we don't have a the voltage is not a function of phi, this term disappears. You'll be left with these two terms right here. Okay, factor out the common terms, you'll end up with this expression right here. Now, this is the electric field defined by A r hat and A theta hat. Okay, to illustrate that, the potential field looks like this. Okay, it's the circles around the charges. These are your equipotential surfaces. The electric field is the black lines. So as you know, the electric field due to a positive charge is always flowing outward, while for a negative charge is always flowing into. Okay? So these are the electric field lines, and notice how they are always perpendicular to the equipotential surface. Okay? So that's how you illustrate the electric field and the equipotential surfaces of an electric dipole. So you can try to do that by yourselves using MATLAB. Okay? So you can verify that. MATLAB has a gradient function. So if you have your scalar field, get the gradient of that scalar field. You can plot the electric field using the quiver function. Okay, so let me write that. So there's a gradient function in MATLAB. Just type gradient basically, and it will give you the gradient of a scalar field. And to plot that the vector field result, you can use the quiver function. Right? You can consult the MATLAB documentation for help. All right. So this is the gradient in different coordinate systems. So again, the gradient quantifies the change in each direction. Okay. For Cartesian, you have the change in the x direction, in the y direction, and the z direction. For cylindrical, there's a change in the rho direction, change in the phi direction, characterized by the arc length of the circle, and the change in the z direction. And finally, for spherical, there's a change in the r direction, change in the theta direction, characterized by the change in arc length due to the angle theta, and the change in the phi direction, which is the differential arc length on a circle that is parallel to the xy plane. Okay, so this is your gradient in different coordinate systems. Now finally, let's look at the energy of this electrostatic system. So recall that when we say electrostatic, we mean that there are no moving charges in our system. So let's consider first an empty space. We want to put charges on each point in space and visualize them as putting the charges from infinity to the point of interest. So to move Q1 to this empty space, we don't need to exert any effort since there is no electric field there yet. So if you move Q1 to that point, we exerted zero effort, therefore the work is zero. When we move Q2, okay, when we move Q2 from negative infinity to this point, right, to this point here, then Q1 has an effect on Q2. Q1 has an effect on Q2, then if they oppose each other, then you're exerting effort to put Q2 from negative, from not from negative, from infinity to this point right here because Q1 emanates an electric field. Therefore, you exert effort equal to the potential difference between 2 and 1. Okay? With Q3, also the same, but in this time, and in this case, you have charge 1 and charge 2 affecting Q3. Q4, also the same, but with 1, 2, and 3 acting on them. And other terms for more charges. So this is the total energy that you need to basically put the charges together near each other on an empty space. So the potential energy then of the system is equal to the sum of the work needed to put everything together. Okay? And it's actually easy to prove that Q2 V21 is equal to Q1 V12. That is, Q2 times V21 is equal to this expression right here. So this is the voltage due to Q1 or the potential due to Q1, which is equal to, which just switch these two together, which is this commutative property of multiplication. And R21 is just the distance between 1 and 2. So that's equal to R12. And that is actually V12 right there. This expression here is V12. Okay. Thus, we can write equation A as follows. Okay. This Q2 V21 excuse me, is equal to Q1 V12. This Q3 V32 is actually equal to uh, Q2 V23. This Q3 V31 is equal to Q1 V13, and so on and so forth. Okay. With that, if we combine equation A and equation B together, we get this expression right here. So we combine that. So just look. All right. We combine that. We get this expression plus this plus this. So Q, the voltage, the charge Q1 multiplied by the potential due to other charges plus Q2 times the potential due to other charges, Q3 times the sum of the potential, sum of the potential of the other charges, and so on and so forth. Okay. Now, acknowledging that some terms would cancel out with each other, no, not necessarily cancel out. If you add all these together, you actually get the expression V1. Okay? If you add that together, all of that until infinity, if there's a lot of charges, you get the expression, the potential V1. Same as is true with Q2, you get V2, and also with Q3, you get V3. Okay? So that becomes, if we have an infinite or n amount of charges, the potential energy in that space is equal to 1/2 times the sum of the charge multiplied by the potential due to the charge. Okay? If we have a continuous system with a charge distribution, then we can get the potential energy in that uh, in that uh, in that volume by getting the volumetric integral of this expression right here. Okay? So using Maxwell's first equation, so this is rho v, your charge distribution, and v, which is your voltage. Using Maxwell's first equation and the equivalence that if we get the divergence of your some scalar field multiplied to a vector field, that is equal to just factoring out this scalar field times the divergence of the vector field plus the dot product between the vector field dotted to the gradient of your vector field. Okay, so I won't discuss where that equation came from. But using that equation, okay, we have this expression right here, our original expression. Substitute the uh, Maxwell's first equation. So your volume charge distribution becomes del dot D. Okay, and using this identity right here, the del dot D becomes this expression right here. Okay, so basically it's just this. Okay, and we multiply or we transpose this term to the other side. You'll end up with this expression inside the integral. And you distribute the integral to both terms, you get this expression right here. Okay. You apply the divergence theorem to the first term in the integral right here. Okay. So we get the closed surface integral of this expression, your scalar field multiplied by your vector field B. So some notes. For the first integral, we chose a surface that encloses all charges. So a surface at infinity may be selected. So you want to enclose all charges that contribute to the potential energy in the system. Since now, if we are going to choose a surface that is at infinity, the potential at infinity is 0. Therefore, this first integral right here becomes 0. And finally, we get this second equation. Since the gradient of V is equal to negative of the electric field, the potential energy due to your electrostatic charges becomes this expression right here. The volume integral of the dot product between the electric flux and the electric field. Knowing that the electric field and electric flux are related to each other, where your electric flux is equal to epsilon sub 0 times your electric field intensity, the work done, or the work stored in a system of charges becomes this expression, 1/2 times the volumetric integral of epsilon sub 0 times the magnitude of the electric field squared. For example, we're interested in calculating the energy stored in the electrostatic field of a section of a coaxial cable length L. So it's a part of your coaxial cable. So knowing that between the conductors, the electric field is this expression, where rho s is the surface charge density of the inner conductor, whose radius is A. We want to know the charge stored, the energy stored in that coaxial cable. We'll just use this expression for the potential energy. Okay? So you integrate that, get the magnitude of E, get the square of that, and you'll get this expression here. So using the bounds of the volume, which is from A to B, the radius, your angle is from 0 to 2 pi, and your Z is from 0 to L. So that's where these bounds came from. And integrate that, get this expression right here. Okay? And the same result actually can be obtained using the original definition of your electric field. Electric field or your electric potential. Okay? The work due to your uh, charges present. Okay? So we define then what we call an energy density. So the energy density quantifies how energy is distributed over a region in space. Basically, it's just a differential work with respect to the voltage. sorry, the volume, not the voltage, sorry, with the volume. So it quantifies how energy is distributed along a space. So recall that we have this expression for your work or your charge stored in a region with charges. Sorry, not charge, work stored, energy stored. All right. So if we get the differential of this equation, the integral sign disappears and it becomes this expression. And we want to get the derivative of your work with respect to space, okay, your very small volume, it's equal to 1 half d dotted to e, or it's 1 half epsilon sub 0 multiplied to the norm of e squared, or the magnitude of the electric field squared. So this is called the energy density of, this is the energy density, the expression for the energy density due to presence in electric field. Okay, and that ends this lecture. So again, if you have any comments or questions, or if anything is not clear, just just post a comment on YouTube and we can discuss. Okay, uh, and I'll see you when I see you then.